Thanks a lot for the introduction, and thanks to the organizers for inviting me. This is my first time in Bonn. It's really nice and nice to see familiar faces again, and also meet some new people. Okay, so just to start with a little background, a 2017 CERN program on geometric structures of information. I gave some talk on the duality between entropy inequalities and functional inequalities in some kind of very abstract settings. And so this talk, and then what got me thinking about that at the time was this paper by Carlin and Courtade on dualities between subadditivity of entropy and Brasquet-Lieb inequalities. And Michel probably doesn't remember, but he asked me a question. After my talk, he said, okay, when is this constant finite? All right, and that motivated about 7 years of studying these inequalities on Euclidean spaces, because this is kind of a nice concrete setting where I was actually able to, answer that question. And so it really got me thinking and thinking about how to, unify what we know, how to explain what we know, and see a bigger structure and kind of the picture that consisted of lots of different independent results. Okay, so in information theory, there's tons of inequalities for entropies and so forth that are largely due to properties of logarithm, convexity, submodularity, whatever. We saw, for example, yesterday, Shearer's inequality as one example, and these types of inequalities generally hold in Polish spaces or whatever. But some very special inequalities are known when we're working on Euclidean space, and I think the prototypical example is so-called entropy power inequality, which we've heard of before, and one form that we can state it as is like this. If x1 and x2 are independent random variables, and I consider independent Gaussians with the same entropies, then the entropy of the Gaussian sum is no larger than the entropy of the sum of the individual random variables. And so for at least the first part of today, but really, I guess, the main question for today is what's the bigger picture here? What can we build kind of a theory and a calculus for working with these information inequalities that capture some geometric structure about Euclidean space? And so I'll start with some notation. I try to be really consistent on the notation throughout the talk, and I've kind of recorded all of the important stuff over here. But basically what I'm going to do is I'm going to typically consider different random vectors and different spaces with given distributions. And then we'll consider couplings of these random vectors. And so I'll use the usual abuse of notation where we let random vector stand for its law and vice versa. So I'll write x is in this set pi of x1 through xk to denote that x is a big random vector that's a coupling of these other random vectors. So namely, the ith component of x has law, or is equal to xi in distribution. And so one other thing that I want to mention, this is kind of secondary, but we can constrain this set of couplings in a way that I call information constrained couplings. I don't know what the best word for it is. But basically what we can do is we can take any function, taking values 0 through infinity, that takes in a subset of indices, okay, and then spits out a number. And what we can do is we can constrain the set of couplings by those couplings whose relative entropies between the joint distribution on the coordinates in S and the product distribution of the coordinates in S is no larger than our constraint. So in the case of, if you're just working with two random variables, this would correspond to mutual information, but it's just kind of more general divergence between joint distribution and the product of its marginals. And so some really simple examples are just if I take this constraint function to be identically 0, then the only admissible coupling is the product coupling. Okay. And then on the other hand, if the constraint function is equal to plus infinity for all inputs, then the set of couplings is completely unconstrained. It's a set of all couplings. And so, the in-between is that I'm just able to constrain kind of the independence, in a sense, of subsets of coordinates. All right, and then more notation that will prevail throughout. Okay, so I'm really consistent on this, that EI and EJ, these are Euclidean spaces. I always try to use the index I for the subscript and index J for superscript. And then basically I collect all these EIs together into one big space E0. And then this bold B is a collection of linear maps that sends E0 to each, oh, this should be EJ. So since we think about EI as kind of the input spaces and EJ as the output spaces, and then I collect these vectors C and D as just coefficients, positive reals. Okay, so just collectively these are summarized as this triple. And so for Euclidean space, I'll just let this PE denote the set of probability distributions with having density in finite second moments. So X, again, I use interchangeably with its law. X being in PE means that, okay, the entropy exists and is finite due to finite second moments. Okay, so the integral exists in a Lebesgue sense. And just in the notation from before, okay, if I've got random vectors that are, live in these spaces EI, then X, a coupling of these is a random vector on E0 with finite second moments. And then kind of the canonical projection onto the ith coordinate is equal in distribution to xi. Okay, so part one of this talk is almost everything I know in one line. And I realize when I wrote this, and now that I say it out loud, I'm not sure if that's something I should be proud about. Summarize everything that you know in one single inequality, but here it is. So basically it's a multi-marginal type of inequality. So I fix marginal xi living in these spaces ei and any kind of constraint function. So in a similar flavor to that inequality that I showed you on the first slide, what this says is that if I look at a linear combination of entropies of linear transformations of the vector, okay, maximized over all of these constrained couplings, then I can find Gaussian vectors living in the same spaces whose entropies match those of the original vectors such that this entropy on the left is like that. So bounded is a lower bound on the other. So it's kind of like a generic Gaussian comparison principle, same as what we saw on the first slide, but now we can introduce kind of arbitrary maps, we can have many different entropies, so forth. We don't require the random variables to be independent, and so on. Okay, so I don't plan to say much about the proof of this because I want to give a different proof later that kind of gives some of the key ideas. But first, what's that? Oh, but first I want to give a lot of examples and consequences of this to convince you that it really does provide a somewhat unified and interesting framework for a lot of the inequalities that we know.
The ZI are independent?
No. So the ZIs are Gaussians that live on these spaces. Okay, the covariance is not determined. In fact, you might have to select the covariances here. But the only thing is that they're Gaussians with entropies that match the xi's. You see what I'm saying? And so you maximize the left-hand side over couplings that are constrained in their dependence, but they'll only be the independent coupling if that constraint function is identically 0. Right. In general, it won't be. Okay, and so even with the applications I give on the next few slides, I think there's just many more interesting consequences just waiting to be written down. The inequality is quite flexible, and so I think that maybe by giving some examples, it'll show what kinds of things can be done, and hopefully it'll be a tool that'll be useful to some of you. So, yeah.
This reminds, of course, I cannot say like that. It reminds famous press complete.
Yeah, okay, we'll get to that. Okay, so first application, I'm going to just copy and paste this theorem up at the top for the next few applications so that we can see how to specialize it, is something called the Zamir-Feder inequality, and it's just a generalization of what appeared on the first slide, and Zamir-Feder said if you have a k-dimensional random vector with independent entries, then the entropy of a linear transformation of that vector is lower bounded by entropy of linear transformation of Gaussian vector with independent entries and whose coordinates match those of xi in entropy. And so this kind of had a one-off proof, and you see that it follows directly from above just by considering one term in each sum. Okay, so there's m is equal to 1. And then I select that constraint function nu to be 0, so that way I force the independent coupling, and I choose all of my Euclidean spaces just to be the R. Okay, so that would be one example. Okay, another example is Brun-Minkowski inequality. So again, by a particularization of the coefficients here, so now I'm just going to allow all couplings. I take a particular linear map. And now, if I take the random variable x to be uniform on some compact set k, or x1 to be uniform on some set k1, x2 to be uniform on some set k2, then we know that the entropies are going to equal the log volume of these sets. And because this convex combination of the x's is supported in this Minkowski sum of the sets, the entropy is upper bounded by log volume of that set because subject to a support constraint, entropy is maximized by the uniform distribution. And so we immediately obtain Brun-Minkowski inequality because the left-hand side is really just something involving determinants with a fixed value. So it specializes to Brun-Minkowski. Okay, and then, these were two extreme cases where I forced the couplings to be, independent, or I allowed the couplings to be arbitrary. But there's also things in between. So, for example, xy random vectors in Rn, finite second moments. We can write down something that looks like an entropy power inequality, but on the right-hand side, instead of looking at the entropy power of independent, or the sum of independent things, I'm allowing them to be dependent, maximizing overcoupling, such that the mutual information between the two things is at most data. So that's just the relative entropy between the joint distribution and the product. And so you get something that looks like this. And, okay, we know the equality cases for this. In the case of unconstrained, it corresponds to Brun-Minkowski, and in the other cases, it's only Gaussians with proportional covariances. And of course, you specialize to force the coupling to be independent. We get the Schoen-Stam EPI. And if I take, I allow myself to look over all couplings, we get basically this entropy inequality that strengthens Brun-Minkowski in a sense. Because if I take x and y to be uniform on, say, compact sets, then this term here is going to be upper bounded by volume of the Minkowski sum to 1 over n. But in general, this won't be uniform on the support. So in some sense, it's a strengthening. Okay, and so the way to think about the inequality above, even though it looks maybe slightly complicated, is it just provides a really graceful interpolation between exponent 2 and exponent 1 as you allow for dependence. Okay, and so this is kind of a question that I mean, I don't know, some people seem to wonder for a while is what's the kind of quantitative connection between EPI and Brun-Minkowski. There's various explanations, but for me, this one's pretty satisfying. Okay, so another application.
So just
yeah.
Which, so you just want to maximize h of x plus y over coupling?
Over couplings of x and y, yeah.
Yeah, is there any hint about what's the best understand assumptions? Or?
Yeah, I have no idea. If x and y, I can tell you what are the extremizers. I know a lot about structure of extremizers in these inequalities. I won't talk about that today, but I'll say that for general marginals x and y, I think the coupling that maximizes the entropy of the sum, I don't know if it has any nice structure, like for example the Brenian map does for W2. I don't know. Yeah.
Because I mean, people study stability in Brun-Minkowski a lot. I'm not saying that this can do it.
Okay, so one more application. So let's talk about what I call multi-marginal entropy inequalities. So basically, look at an inequality of this form, and you want it to hold for all choices of marginals, and you ask what's the best constant b in such an inequality. Well, the comparison principle from the previous slide, or from the first slide, or whatever it was, immediately tells us that we only need to consider Gaussians here. Okay, so that Gaussians saturate this, this inequality. Okay, so we have the sharp constant is equal to the sharp constant for Gaussians. Okay. I won't talk about conditions for finiteness, but this is related to Michel's question that I referred to earlier. We know necessary and sufficient conditions for this to be finite also. And just as a few examples, you know, there's this paper by myself and Jingbo where we consider the case of unconstrained couplings, and there's another paper by Anantramjag and Tranjornea that consider the case of independent couplings, and the two results follow directly from kind of these extreme cases. Okay, and so now let's talk about duality. So there's a well-known relationship between entropy inequalities and functional inequalities. And so the dual formulation of those multi-marginal entropy inequalities is precisely this functional inequality here. So if you have non-negative measurable functions f and g, okay, f is a function from ei to r, and g is a function from ej to r. Okay, if they satisfy this pointwise inequality, then you can upgrade it to this inequality, basically of norm inequality. And we know that the inequality is sharp for this constant, and it's saturated by Gaussians. And so the weak duality direction goes from entropy to here, but this is completely equivalent. The other direction is a little bit more difficult, but you can go back. And I just want to also maybe mention that Cordero, Askin, and Mori considered functional inequalities kind of this form under specific assumptions on the linear maps. And I mean, they didn't explore the duality here, but I just want to point out that they did consider these types of inequalities. So now back to your point. Okay, of course, now of this general class of functional inequalities here, you know, we can specialize it to obtain, you know, various well-known classes of functional inequalities, like the Broskamp-Lieb inequalities, okay, which were inequalities of this form. Okay, it just corresponds to taking one function here on the left-hand side, because if there's only one function over here, then obviously I just want to take it to be equal to the right-hand side, okay, to give me the best bound. Okay, so that's it, and basically that duality then just corresponds to this paper that I mentioned earlier by Dario and Eric Carlin that really inspired me to start thinking about this duality. Okay, and then there's also these so-called reverse Broskamp-Lieb inequalities that, you know, by Barth in '98, and okay, this corresponds to just taking a single function on the right-hand side. And then in 2022, Barth and Wolf considered a different class of inequalities that it looks a little bit mysterious in their paper, but when you look at it, it's really of this form, and they showed that these inequalities are saturated by Gaussians. And this is, again, a special case where basically you just allow one of the functions to depend on all of the variables. So you just kind of augment the datum, so to speak. And so there's many other consequences of, you know, the inequalities I listed, of course, things like Young's inequality, reverse Young's, there's these chain Daphne's Peoris inequalities that are a special case of this. I think that in large part motivated Barth and Wolf to consider these. But basically they all fall in this hierarchy. And so now there's actually, when we start looking at this general class of inequalities and want to develop like a calculus for working with them, it turns out that there's even more structure. And so if I think about that collection of linear maps as a big matrix that sends E0 to E superscript 0, which I'm defining as the direct sum of the output spaces, then I can consider the transpose, or the adjoint, that sends E superscript 0 back to E sub 0, and okay, this gives me some other linear maps here. Okay, and if I just rescale things correctly, I mean, we don't need to worry about it, but if you rescale things correctly, then we get two different versions of these multi-marginal inequalities. The first one is where I select marginals on these spaces EI and consider couplings. Okay, and then the second inequality is just completely different, where I consider marginals on the output spaces EJ, and I consider the linear transformations under these adjoint maps. Okay, and then we know from the previous result that both of these inequalities are saturated by Gaussians. So just by definition, the sharp constant is this, you know, constant that we get by considering Gaussians. And so what's special about these inequalities? Well, right now I just wrote down two separate inequalities for different choices of spaces and different maps, although they're related in some way. And so it turns out that we should think of these two different data here and here as dual in some sense, in the sense that for these two different data, the sharp constants are equal. And this is a little bit surprising, I think. And it turns out that it's not too deep in a sense once you have the Gaussian saturation, since dg is basically just a function involving quadratic forms. Basically this duality result corresponds to duality of quadratic forms. And this really generalizes this somewhat remarkable and to me initially mysterious result by Barth that the sharp constants and the Braskamp-Leib and Barth inequalities were equal. Okay, because precisely the dual data for a Braskamp-Leib inequality is the data for a Barth inequality. Okay, and so what you can think about is, these were the two extreme cases, and now you have this general duality. And it's kind of nice because now this class of functional inequalities is closed under this dual operation. And just as like a comment about a tool, it makes trivial work of proving sharp constants in some inequalities. So for example, let's say I want to look at this entropy inequality on the first line and I want to determine the sharp constant there, d. Okay, so it turns out d is equal to 0, but suppose I don't know that. This inequality is dual of Prokop-Leibler. Then I look at the inequality for the dual data, and it reduces simply to h of y1 less than or equal to h of y1 plus d. Okay, so what's the sharp constant? D is 0. So you can immediately, if you know one inequality, you can immediately write down another one. And so just for visual context, I really like this figure from Gardner's 2002 survey on Brod-Minkowski inequality, where he basically explained Brod-Minkowski inequality and put it in the context as kind of hierarchy of other inequalities. And this also was really what inspired me to start thinking about the hierarchy of inequalities and the structure and how things are related. And so if we just slide this inequality, this figure down a little bit, now we can add in all these other things up here. Okay, so there's this multi-marginal inequality that basically implies Barth-Wolff and Entropy-Jagner, okay, the consequences of these, or Braskamp-Leib, so on and so forth, okay? And so we can, think about going to the top of the hierarchy here. And what I think is cool about this idea of dualization is I can, within each of these classes, I can consider the somewhat like the notion of dual data. Okay, so multi-marginal inequality, it's closed under this dual operation. So, I take the dual, I get another multi-marginal inequality. That corresponds precisely to the duality between sharp constants and Braskamp-Leib and Barth inequalities. But for any other inequality that I have in this hierarchy, for the most part, I can write down a completely dual inequality that has some different form. That's somewhat surprising. For example, reverse Young inequality, in this paper with Jingbo in I think 2020 that I referred to earlier, we wrote down what the dual form of this reverse Young inequality should be, and it turns out to be something that seems new, but you can write it down with sharp constant. Okay. By the way, I should mention that the entropy inequality falls in this hierarchy. Like down here, and also the Entropy-Jagner inequality. And just, thinking about the entropy power inequality, it's somewhat reflexive under this dual operation in the sense that, anyway.
What are the numbers here?
What's that? These numbers were from Gardner's survey, and they're referring to, this figure was taken from his survey, so they're referring to the equation numbers in his thing. Yeah, these numbers are not important for us. Okay, so what I want to talk about now is part 2 of this talk. So that I just kind of wanted to say what's the status of kind of what I consider to be the general state of things. And now I want to talk about a different class of inequalities, basically hologram type inequalities that relate relative entropy to the Wasserstein distance. And then I'll talk about how these relate back to these other inequalities I mentioned and try to put things in a bigger context. So, okay, suppose we've got fixed weights lambdas. Okay, so they're just non-negative, they add to 1. And I'm going to take these spaces EIs to be all of the same dimension. Then Kolesnikov and Werner investigated what they call a Talleyrand type inequality for Wasserstein barycenters, which is just an inequality of this form. So Talleyrand inequality so that relative entropy controls Wasserstein 2 distance, or Wasserstein P, or whatever, but usually Wasserstein 2. And here kind of we get the same thing morally, except for on the left-hand side, what appears is instead of Wasserstein 2 distance between a measure and Gaussian, this minimization problem, which is referred to as the Wasserstein barycenter problem. So you try to find the measure that somehow is close to all of your, I didn't say given, well, okay, anyway, close to all of your given measures mu I. Okay, and so the optimal solution to the problem on the left-hand side, it always exists and is unique, and it's called the Wasserstein barycenter of these measures mu I with respect to the weights lambda. And so one of the results in our paper is that they show that this inequality holds whenever mu I are unconditional measures. And I guess most people know here knows what unconditional means, but it means it's symmetric across every coordinate axis. So if I flip any coordinate of the random vector with that distribution, then it doesn't change the distribution. Okay, so that was kind of their result. And yeah, oh sorry, I didn't need the weights lambda here yet, so my apologies for the extra information. And then very recently, I think maybe just a month ago or so, there's this paper by Nakamura and Tsuji, who were kind of inspired by this Kolesnikov-Werner paper, and I'll talk a little bit more about what they do in a second, but they showed that in fact this inequality holds whenever the mu i's are symmetric measures. Okay, so you just, yeah. Okay, and in fact, Nakamura and Tsuji consider what they call a generalized Legendre duality relationship. And so they consider this problem. For Q, a symmetric matrix, what's the sharp constant D in inequalities of this form? So you suppose that you've got some functions, okay, that are lower bounded by this quadratic form on the right-hand side. And you ask, okay, what's the upper bound on the norms? And so their main result is that if you restrict attention to even functions f, then this inequality is saturated by Gaussians. Okay, and then what they do is they invoke kind of some duality results from Kolesnikov-Werner to show that their Wasserstein barycenter holds for all symmetric measures. Okay, so that's how you get the other result on the previous slide. And so, you know, this idea of entropic duality between these Wasserstein barycenter problem and the kind of generalized Legendre duality relation, I mean, this was to a certain extent explored in Kolesnikov and Werner, but it wasn't quite written in exactly this form, but this form is kind of trivial. But really, this generalized Legendre duality relation, okay, if I'm looking for the sharp constant, then it turns out it's completely equivalent to this multi-marginal entropy inequality where on the right-hand side, instead of maximizing linear combinations of entropies, I'm maximizing some quadratic form over couplings. Okay, and generally, like if Q is positive definite, then I think this is no problem to solve using existing results. So generally, the interesting case is when Q is non-definite or indefinite, I guess. Okay, so what does Q barycentric mean? It's I put a star there because I don't really want to go into it, but it just means that if you look at the barycenters of the measures who have density proportional to e to the minus fi, then I form the vector by collecting these barycenters. Then it should lie in kind of the cone of vectors x such that qx inner product of qx is equal to 0. So it's some sort of alignment of the barycenters of these measures. Okay, so it turns out that using roughly the same ideas as we did to prove the Gaussian saturation of these multi-marginal entropy inequalities, at least from a 20,000-foot view, we can establish this multi-marginal Wasserstein barycenter inequality in complete generality. Namely, we can consider arbitrary weights, okay, lambdas. It turns out these are the right coefficients to have. And measures that don't need to be symmetric, okay, just centered. And if you can relax the centering also because you just add a correction term that depends on the means. So this is kind of the most general form, really. And also we can give precise equality cases for this. Okay, so really again, just to remind you, Werner and Kolesnikov's results correspond to the special case where all the weights are equal and mu I is unconditional. And then Tsuji and Nakamura's result, they established a case for equal weights and mu isometric, but if you really look at that duality relationship that I told you, that I just showed you on the previous slide, then you can infer the case for non-equal weights from their paper also. But really the restriction there is the symmetry of the measures. And so, maybe it's just worth mentioning that Kolesnikov and Werner give several applications of these types of results in convex geometry, and now so the conclusions of those results in their paper extend to a case without any symmetry and with unequal weights and so forth. Okay, so the functional formulation is this. Okay, it's this kind of generalized Legendre duality relation for a very specific quadratic form on the right-hand side. And kind of once you fix a quadratic form, it tells you what the coefficients on the left-hand side sort of have to be, in a sense. So really we should think about this as Nakamura and Tsuji's generalized Legendre duality for specific quadratic form on the right-hand side that looks kind of like a rank 1 matrix, except for with its diagonal entries deleted. That's really what it is. And then Nakamura and Tsuji's results, again, just at risk of repeating myself, it would imply exactly the same thing, but only under the assumption that the FIs are even functions. And so to me, this suggests that really the symmetry assumptions are not essential here. I think it's an artifact of their proof. And in fact, I have some progress towards removing that assumption on the result in general, but it wasn't quite ready for presentation today, so maybe next program for the organizers. Indirectly. Okay, so now, so I should at least give some proofs in this talk. So let me give the ideas behind this proof. So first idea is there's a structural relationship between Wasserstein barycenters and multi-marginal optimal transport, and this is pretty well known. In this paper by Agwe and Carlier in 11 and Jingbo and Switch in 98. I don't know if I pronounce those names right. Hopefully it's good enough. Okay, and basically what they say is the Wasserstein barycenter problem on the left is related to this optimal transport problem on the right in the sense that their objective or their optimal values are the same. And something else surprising emerges here, that if I take the optimal coupling on the right and I push it forward by this basically averaging map by weights lambda I, then I get the barycenter for the problem on the left. Okay, so it's kind of cool. And so a completely equivalent formulation then of this Wasserstein barycenter problem is this kind of entropy multi-marginal problem that involves entropies and a multi-marginal optimal transport problem. And so it's just this. It's just writing down what we're after, now in terms of multi-marginal optimal transport. And so the second thing is so-called displacement convexity of the Wasserstein barycenters. And so this can be found again in this Agwe and Carlier paper. And so the point is that this Wasserstein barycenter enjoys some notion of displacement convexity. Okay, so this is it. Sorry, this should be just a mu here, because I said mu denotes the Wasserstein barycenter, so ignore the star there. Sorry about that. If that's the first typo in the talk, I'm doing well. But it's probably not the first one, which means the audience is not paying close attention. Okay, so anyway, just using this connection between the Wasserstein barycenter and the multi-marginal optimal transport problem, if mu is the Wasserstein barycenter of the mu i's now with respect to weights lambda I, then really this displacement convexity inequality can be written in this form. And this, so the next thing that we need in addition to this displacement convexity is a so-called symmetrized telegram inequality. So this has kind of a long history. It was written first in this form by Max Fati in a 2018 paper. But in fact, it's completely equivalent to something called the functional Blaschke-Santalo inequality. Okay, that goes back to Ball and I think 86, at least in the symmetric case. Okay, but in the general case, Wasserstein, Avidan, Courtade, and Millman in '04, and then there was a paper by Gozlan on Talagon type inequalities that talked about duality between optimal transport or Talagon type inequalities and entropy inequalities, functional inequalities, and somehow this also can be distilled from the results there. So it's got kind of a long history. But I want to give a proof today because we recently published a paper where we came up with a quite short proof of this. It's really quite cute, I think. And so the proof is based on martingale ideas, and then what I'm presenting here today uses a suggestion that Joseph Levesque gave us to further make it even simpler. Anyway, prior to this, even the simpler proofs of the functional Blaschke-Santalo inequality were quite tedious, I guess. I mean, the short ones were a few pages at least. So the key idea is that for entropy, relative entropy, we have a variational representation. Namely, if I give you a Brownian motion, then I can write 2 times the relative entropy as the minimum energy of a drift U. Okay, and so by drift U, I mean it's adapted to the filtration of B, and the drift should be such that when I look at the resulting Ito process at time 1, then it has law mu. Okay, and without loss of generality here, because my measure mu I'm taking to be centered, I can assume the drift is 0 mean, because if it's not 0 mean, I can always subtract off its mean, and that will reduce the energy there. So this is a variational representation of entropy, so-called in terms of so-called Fulmer drifts, just a consequence of Birsenhoff's theorem. Appears in a paper by Joseph Levesque and earlier by Fulmer. And so now the key idea is we can take a reverse Brownian motion, B hat. Okay, so I'm just doing the time reversal of B. And so that's another perfectly good Brownian motion. So now I'm going to take the representation of the relative entropy of nu with respect to gamma. Basically the same thing, where now I'm just considering drifts adapted to B hat. Okay, so this is driven by a different Brownian motion. And I claim that we're done now. Okay, so take U and V as this. And so the first thing to note is B hat 1 is equal to B1, just by definition. So the W2 distance is upper bounded by this quantity because this thing here is integral ut, let's say, plus B1, okay, which has law mu, minus integral Vt plus B1 hat, which is equal to B1, so it cancels, which has law nu. Okay, so that's just an upper bound on the Wasserstein 2 distance. It gives us some coupling. And now I just rewrite this integral. I just switch the variable Vt to V1 minus t. That doesn't change the integral at all. And I pull it outside by convexity. Okay, and once I do that, I just evaluate this expectation, which turns out to be super simple, because the cross term goes away. Because the cross term involving expectation ut and v1 minus t, well, each of these are 0 mean, so it's a covariance between them. But they're actually independent, because ut is adapted to b, so it depends on the Brownian increments just up to time t. And vt is adapted to b hat, and so v1 minus t just depends on the Brownian increments after time t. And they're independent. And that's it. So the proof is done. Okay. Amazing, right? Yeah.
I don't know.
Oh, you looked like you had a question.
No, it was just time. Okay.
You just what?
No.
Okay. So this is cool. So maybe just as a meta comment here.
I'm giving the coupling, which is, so this is the coupling which satisfies the inequality. Right? This is the, so you do the Lehec coupling, and are you saying that coupling between mu and nu satisfies the inequality?
So here, I mean, I'm just giving you a coupling. So of course it's greater than or equal to the W2 distance.
I mean, the coupling coming from
the coupling coming from this idea of taking a drift with respect to the forward Brownian motion and another drift with respect to the reverse Brownian motion. Yeah, of course. So it gives you some notion of strengthening, but I have no idea how to compare that coupling to the W2 coupling.
No, that is not.
But so the other thing, just as a meta comment, I'll say that this stochastic idea for proving functional inequalities is really powerful. I've used it quite a few times now over the last several years. I really like it. But always the proof technique is to take drifts that are driven by linearly coupled Brownian motions. So in some sense, you're fixing the filtration of your space. And here, the key new idea is that you optimize over filtrations in a sense as well. That because I'm taking two different Brownian motions, these drifts are adapted to two different filtrations. And in fact, if you take the drifts adapted to the same filtration, then it turns out that this approach will fail. Okay, so
maybe the question was, you can take after the infimum of U and V independently.
yeah, right. Yeah, you can take the infimum over here because, I mean, it's just the two separate things, right? Yeah, I mean, the conclusion is you have that inequality for any, drift U and V that give the correct laws, right? And yeah, you don't. Yeah, in fact, the optimal drifts have a very specific form. It's an explicit function. It's gradient of log of the He semigroup at time at time 1 minus t applied to the density with respect to Gaussian. It's just an explicit function. It turns out to be a reparameterization of the de Bruijn identity, actually, to Brownian bridge. Okay, so now let's go back to this proof of Wasserstein barycenter inequality. And so the key idea is a really simple one. It's just a kind of structural decomposition of this quadratic form. What I'm going to do is just, and these xi's are just numbers now, I'm just going to write it in as I've written, where xn plus 1 only appears in this term here. Oh, maybe I should start. I don't think I said it out loud. So the proof is by induction. Okay, case for n equals 2 is really the base case. And this is just the symmetrized telegram inequality. Okay, so what we do is now we're going to induct. So let me renormalize my weights. So that way the weights lambda I prime from I equal 1 to n add up to 1. Okay. And then basically what we're going to do is apply induction. So the key step is just a decomposition of this quadratic form into, I mean, it's essentially Pythagorean theorem. And so xn plus 1, the new variable in a sense, just appears in this term. And then also what appears in this term is something that looks like a barycenter, at least deterministically. And then I get this other term over here. And so now what we do is we just write this multi-marginal optimal transport problem, and I can upper bound it as follows, where U is the Wasserstein barycenter of x1 through xn. And the reason why I can write it like this is because I'm basically just fixing the coupling on x1 through xn to minimize this. And then what I do is I'm just going to couple xn plus 1 with the barycenter. And the key thing is that the coupling that minimizes this has, under this map, push forward of the coupling under this x bar map gives me the Wasserstein barycenter. So this is precisely the Wasserstein barycenter. Okay. And so really we get this. And now let me just rewrite this at the top so that way we can go from there. And now the next step is we just apply symmetrized telegram to this first W2 term. Okay, so that just splits as follows then. Okay, into the sum of two relative entropies. And now the next step is I apply displacement convexity. Okay, but the thing is that this relative entropy term with involving the barycenter, it together with displacement convexity, sorry. Displacement, did I delete something? I should have some other sum of di's here. I think I wrote the exact same thing. Oh, no, there is that, right there, sorry. Yeah, I was just getting confused. Yeah, I used displacement convexity on that barycenter term, and that just takes care of some of the coefficient in front of this multi-marginal transport problem. So there's still some of that left over down here. That's where the coefficient comes from. And then, okay, I just apply my inductive hypothesis, and it turns out all the coefficients work out perfectly, and that's what I get. So this is the whole proof of this general barycenter problem. And I think that, just if I'm going to reflect for a second, the reason why I chose to do this proof is, A, it's a new result, but it also highlights, I think, some of the ideas in the proof of the general multi-marginal inequalities involving just entropies and not quadratic forms. That roughly, the idea is that Gaussian extremality is shown on specific instances of the problem using like a stochastic approach, or maybe heat flow or something else. I prefer the stochastic approach. And then it requires some insight to develop a somehow structural decomposition of the problem. Here it manifests in induction, but in the other problem, you kind of can split the data into different complementary data in a sense. And so roughly the program is the same, at least from a high level. Okay, and then, yeah, okay, so let me maybe make a few comments now. So the status of things is that we know all of these kind of multi-marginal inequalities like above are saturated by Gaussians. And under certain symmetry or structural assumptions, this kind of dual formulation of the Nakamura and Tsuji generalized Legendre duality is also saturated by Gaussians. Okay, in the sense that if I consider xi's to be symmetric and centered. Okay, for example. And both of these have precise dual formulations as functional inequalities. And so if we want to think about the next step towards building a general program, really it should all be unified under a common framework that looks like this. That I want a multi-marginal inequality where I bound entropies by supremum over couplings of something involving entropies of linear transformations and some quadratic term, okay? And I'd say that I really expect Gaussian saturation in this whole class of inequalities, okay? And in fact, I can prove it in many cases. So I have a lot of progress towards this, but I can't stand up in front of you today and say for sure that that this whole class of inequalities is saturated by Gaussians. And if it was, it'd be really nice. It would imply, you know, these Brus-Kemp-Leib inequalities, Barth inequalities, everything in between, this generalized Legendre duality, so on and so forth, and all, you know, combinations of those. Okay, and so I think that that's really what I'm after these days, is thinking about this problem. Okay, and then, yeah, so maybe I stop there. And I think the talks are supposed to be 50 minutes, and it's 9:49, so.